All right, so I want to talk about evaluating technologies, evaluating energy technologies, and specifically, oh, right. Specifically ask the question, can data-informed mathematical models help to accelerate technological development? So this is the idea behind directed innovation, which I mentioned during my introduction, where we're asking the question, can we basically predictively evaluate technologies? And of course, the answer is no, we can't do that, there's always going to be inherent uncertainties. But I think there are some things that we can say about how different technologies compare. And it's really important that we try to do that because of the nature of this problem, because we have limited time, we have limited financial resources to address this problem. It doesn't mean that all innovation should be directed. There should certainly be a lot of curiosity-driven work out there. But I think there are some things that we can learn from looking at the data and modeling these systems, the systems in which technologies are used, and also limitations of technologies, as well as why some technologies improve more quickly than others. And so I'm going to, rather than talk about this in the abstract, I'm going to talk about a couple of examples. And I'm actually going to focus on energy storage, because I think this is one of the big technological challenges that we need to solve. I usually say, in a decade or 15 years to get on the path that we want to be on to decarbonize. And so just so you can place this kind of work in the broader context of research, we can think of this as studying innovation from an engineer's perspective. So trying to understand technological innovation, how technologies are improving, how we need them to perform, but then feed that back into the design of technologies and also into decisions that private investors and policymakers have to make. Okay, so let me start first with the example of stationary energy storage, and then I'm going to go to mobile energy storage. And I'm going to put out there, I'm going to posit that we can't evaluate storage technologies without understanding patterns of demand and also patterns of electricity price. And in a lot of the work that we do in my lab, we're focused on the performance intensity of technologies, and performance intensity from the perspective of investors. I often say the clean energy transition will not happen unless investors decide to adopt clean energy technologies. And those investors can be utilities, they can be private citizens purchasing vehicles, for example. But there's also another side to the costs of a technology. So I just want to write a short, very, very simple expression it's more conceptual for thinking about how to evaluate technologies based on their performance. So we talk about performance intensity, and that's usually the cost of a technology per unit of service that it delivers, plus some externalities. And this is what an investor sees in a competitive marketplace and makes decisions based on this. But there can also be externalities. Those could be integration costs, system-wide integration costs. Those could be emissions impacts and economic costs, or we may even want to evaluate this in a multi-dimensional space, not necessarily converting everything to dollars. But this is kind of a very general expression that we can use to evaluate technologies. And I will posit that no technology will take off in a competitive marketplace unless it competes favorably with other technologies along this metric here. And it can compete favorably by providing a better service or by providing the same service at lower cost. And so this is, as engineers, we're often focused on improving this here, but also when we take broader societal goals into account, we want to focus on the externalities as well, and that's also what policymakers want to focus on. Okay, now I'm going to talk about storage, focusing, so that I can give some specific examples, focusing on this. So the view of how storage technologies are performing from the perspective of potential investors. And we're going to ask, in the case of stationary storage, how close are these technologies to being competitive when coupled with renewable energy? And how can we compare different energy storage technologies? And this is an interesting research question, as I mentioned at the beginning of the workshop, because we have a diversity of different storage technology options. And evaluating their costs on a common scale turns out to be a non-trivial thing to do. So when we talk about the two main dimensions, when we talk about the cost of storage, stationary storage, there's two main dimensions of these costs. And they're both capital costs. There are also some operational costs, but the capital costs tend to dominate. We can also call them capacity costs. And so those would be the power capacity costs. So we can measure those, for example, in units of kilowatts of capacity, charging or discharging. And those two are a little bit different because you have a round-trip conversion efficiency and some losses. And then the cost of energy capacity, which we often measure in, dollars per unit energy storage. So this isn't an operational cost. It's the energy capacity cost of the storage. And so hypothetically, you can think of any storage technology. A hypothetical storage technology could be anywhere in this space. Where these technologies are today are sort of, they're in various places, kind of relative. I'm not going to put any numbers on here, but we can talk about the relative positions. So, for example, we have compressed air energy storage and pumped hydro are up here. Batteries are sort of out here. There's lots of different options for batteries. So there's a real diversity of options. And so you might notice that, okay, we want to get to the origin, but there's no single technology that dominates, right, along these two dimensions. And so therefore, we have to look at the service that storage would be providing. I should also say that the reason pumped hydro and compressed air energy storage is up here and batteries are down here can be traced back, at least in part, to the physical kind of design and the physical limits, the physical laws that we're using in these technologies, where in the case of pumped hydro compressor energy storage, you pay very little for that energy capacity because you're basically using the capacity that Mother Earth has given you, right? So you're looking for those underground storage caverns and that topography of the landscape that allows you to inexpensively build pumped hydro storage. So we have, different kind of data points. There's regional variability. There's also a lot of uncertainty in the cost because there's poor data quality in this area. And actually, at the break, we're going to have a little expert discussion and elicitation to try to refine these numbers a bit more. But in any case, so pumped hydro storage up here, we have a number of batteries here, lead acid, and so forth. And here, you're really paying to build that energy capacity, right? So there's some costs. With the flow batteries, some would say that you can really bring that cost down, and there are some other advantages in terms of economies of scale and so forth. Okay, so how are we going to compare these technologies? We have to look at how they're used, and in a recent paper, we looked at one application, which I think is a potential early use of storage for renewable energy for various reasons, in part because it's not a very difficult prediction problem, but where you're basically selling electricity from your solar or wind plant when the price is high. And it turns out, so what I'm going to draw on here are lines of constant value. And I'm happy to share this paper with anyone that's interested as well. But it turns out that the slope looks something like this, right? So you have some of the data estimates for pumped hydro and compressed air energy storage are kind of below this threshold. And what I'm showing here, we also have to look at which energy resource we're using. So this is the line for current wind generation costs or current solar generation costs. They're actually a little bit different, but the slopes are very similar. And so basically this tells us that these lower energy capacity costs, higher power capacity costs technologies perform better in this context. That's because you want to have enough energy capacity to be able to take advantage of your price spikes. It also turns out that there's an interesting emergent property in the electricity price time series that means that these slopes are very similar across locations. And so that means that results like this can inform broader research agendas. So that's one way in which we can use models of how storage technologies are going to be deployed and used in order to inform technological development. This can also give us cost targets for storage. One thing I want to point out is that as the cost of solar and wind falls, this line is going to move toward the origin. This means that storage technologies have to fall at a pace that keeps up. They basically have to keep up with falling renewables costs in order to continue to add value. And so that's an interesting angle that we wouldn't see without looking at the problem from the investor's perspective. And of course, there are always policies that could come in to correct this. And, but just working with the system that we have now, we really have to look at the individual investor's perspective. So anyway, so this gives us cost targets for storage technologies. It does highlight some of the benefits of storage technologies that can give you low energy capacity costs. Furthermore, I expect, and I haven't shown this yet, but I expect that this line may become steeper over time as we look at storage providing other kinds of services that would be needed to deal with an intermittent renewable supply. So anyway, so that's one example. And then how much time do I have left?
We've got about 2 minutes.
2 minutes, okay. So just very briefly, I want to talk about storage for vehicles, for electric vehicles. And this is I'm going to show, again, a specific example. This paper will be out next week or the following week. And what I'm going to show here is basically, so in the case of mobile energy storage, energy density and specific energy become very important. So the energy per unit volume, the energy per unit mass become very important, right? And so what I'm going to show here is basically where we are today if we plot specific energy, so energy per unit mass for the best batteries out there. These are lithium-ion batteries, and the percent of gasoline that can be displaced, so the gasoline substitution percentage with current batteries and then with future batteries. And what you see here is that, so I'm going to draw the curve. It's a little bit different for urban and rural areas, but I don't have time to go into that. But what you see here is that you have diminishing returns to battery improvement. This is based on a study that actually took about 4 years. We reconstructed on a second-by-second basis the drive cycles of people across the US, across many different cities, different socioeconomic classes, to understand how many vehicles could be replaced with a below-average cost electric vehicle with current charging infrastructure. So basically once daily charging. It's a conservative assumption in terms of the ability to charge. And where you are today is, sorry, I'm just going to check one thing here. So where you are today is about, for the US as a whole, is at about 60%. Now, to reach that number, you would need to, I mean, this is just looking at a single day, so replacing vehicles on the road on a single day with this below average cost electric vehicle. So there are some challenges to that. If you really want to reach that full amount here, you may want to enable car sharing and so forth. But where you are today is at about 60%. If we reach the ARPA-E target, we get to about 85%. But then you have this diminishing returns problem, and it's very difficult to get that last 10%. And there may also be some challenges in making sure that internal combustion engine vehicles are available for use on days when you're likely to exceed your battery range. But this again demonstrates the need to really understand patterns of energy demand in order to inform technological development. I think this also, for me, demonstrates what I said earlier this morning, that regardless of the scenario, this is, by the way, just light-duty vehicles, personal vehicles, regardless of the scenario, we're likely to need a higher energy density fuel to meet that remaining 10%. But this can tell us how much batteries have to be in order to get to what level. Interestingly, and this is a little bit counterintuitive, these numbers are not all that different across different cities. So they hold in dense cities, they hold in sprawling cities. The reason is that although the energy per capita consumed in sprawling and dense cities is very different, because of the probability that you would own or drive a vehicle on any given day, if you are driving, you're driving somewhat similarly for the majority of cars on the road. At the tails of these distributions, you start to see some differences. Anyway, so let me wrap up here and just say that, you know, bringing this back to kind of looking forward, I think there's a lot of areas in which we can inform technological development. Energy storage is a prime example, but there may be others, by understanding patterns of demand, and that we can really approach this question as a science to ask, how do we need our technologies to perform? How can we design them so that they can improve more quickly? I didn't have time to talk about that work, but there are some tools that we've developed to address scalability of technologies, how close you are to a commodity cost floor, whether you're likely to see steady or erratic improvement over time that could be applied to any technology. And I think this can help us evaluate technologies ex ante or in advance while they're still in the early stages of development, as well as to inform policy decisions and private investment decisions. So I'll stop there.